Well, this is a first. I'm going to teach class and I've got an empty room, y'all. But that's okay. As always, I'll be throwing this up as a recording, so everybody can benefit it even if they couldn't make it. So let's talk about the real order of operations. So one of my biggest pet peeves is actually the way that most math teachers teach the order of operations. They give students this little mnemonic way to remember the order of operations as a step-by-step process. And I've got a couple of problems with the mnemonics that they use. So if you memorize the order of operations as PEMDAS, please excuse my dear Aunt Sally, sometimes we say that, and the steps that go along with that. That is not the method I'm going to use. And there's a reason why, I promise. It's because learning PEMDAS will lead you astray in two different ways, and I'll discuss those two as we come to them. If you have no idea what I'm talking about, you're like, PEMDAS, what? What in the world? What are you talking about? Please excuse who? Then you're actually at the advantage here because you don't have to unlearn something that doesn't always work. So we need a system that always works. So first of all, let's talk about what the heck the order of operations even is. So the first thing that we are going to need to recognize is that in the world of math, it's a little different than the world of reading because we do not necessarily work math problems from left to right. You guys assume, and in fact, instead of saying work math problems, which is kind of a generic way of saying this, I am going to say simplify, which is what you guys are usually referring to. We do not necessarily simplify math problems from left to right. Now, sometimes, quite by accident, they end up being from left to right. So I'm not saying it never happens, but that's not the order we follow. That is not the order we follow. Instead, in math, whenever, every single time, this is not a sometimes rule, these are not certain kind of problems, but whenever you have more than one operation, you might be thinking, what the heck are you talking about, Kate? What's an operation? Operations are the things we do with numbers in math class, like we add them together, we subtract them, we multiply and divide them. We raise them to powers and we root them. There's even other operations that you'll learn as you get higher in math, like absolute value is an example. And there's more, but we'll just leave off on that. So whenever you have more than one operation in a single problem, a single expression, you need to follow the order of operations. When you simplify. Okay, so the order of operations has 4 steps. And that's a really important thing to understand. So let us look at the 4 steps to the order of operations. So step 1. The first thing you should do when working any multi-step problem in math class or any multi-step expression in math class is you should take care of any groupings. Now, there's a lot of ways that we show or express groupings in math class. Some of y'all were taught that the first step is parentheses. That's one of the dreaded things I hate about PEMDAS. And it is true that one of the ways that parentheses can be used is to create groupings. Okay, so how do you know that something is grouped using parentheses if there is something to do inside of a parentheses? For example, in a problem like this, there is a grouping here. You can see that inside of this parentheses, there is something to do. So if I were going to work this problem, that would be the first thing I would do, the work inside of the grouping. Okay, so yes, parentheses can be used to group. Okay, But those are not the only kinds of groupings. Any teacher who limits you to just parentheses is not doing you a favor. So another way you might see things just being grouped in math class is using brackets. There's absolutely no difference really between brackets and parentheses. They do the same kind of math. They're used for grouping. Okay, but you could also see things grouped on the inside of anything, really. Like you might see a problem on the inside of a square root symbol, and there might be work to do in there. Like, I don't know, 9 minus 5 might be inside of there, and you would want to start on the inside of your grouping first. You could see things grouped with fraction bars. A fraction bar naturally groups things into a top group and a bottom group. There might be work to do on the top and work to do on the bottom. And so I have a natural grouping of a top and a bottom. There's lots of other ways to group, but you'll see that numbers will be set apart from other numbers using some kind of a symbol. They're grouped together. You're going to have to deal with the grouping before you can do anything else. So that's step 1 to the order of operations. Step 2 to the order of operations is exponents. But I want you to be really, really careful, because operations always are on the same step as their inverses. So when you think of exponents, you need to think of 2 kinds of operations. Both the little floating numbers, we often call them powers. So powers count as exponents, but so do their inverses. Their opposites. The opposite, for example, of square would be square root. So both powers and radicals fall into this category of exponents. So that's the second step, exponents and their inverses. Powers and their inverses, okay? So then the next step is multiplication and its inverse. An operation and its inverse, its opposite, always happen on the same, are always part of the same step. Now you might be saying, Kate, what is the inverse of multiplication? Well, let's think about it. Like if you were to put together 5 times 6, you were to multiply, you would get 30. If you wanted to break that number back apart, you wanted to take the 30 and break it back into 6 parts, you'd have to divide by 6. The inverse or opposite of multiplication is division. So multiplication and division are part of the same step. And so it's important to know that since multiplication and its inverse are part of the same step, if you see both of these happening in the same problem and there's a question of order, you should work them from left to right, which is my second problem with PEMDAS. Students who learn PEMDAS think that multiplication comes first and division comes second. That is not true. Multiplication and its inverse are the same step. So they're going to be worked from left to right if they appear in the same problem. And then their fourth and final step is addition and its inverse. So what is the inverse or opposite of addition? Of course, that is subtraction. Okay, so addition and its inverse, subtraction are the fourth and final step. They're going to be the last thing that you do in any problem, unless it's been grouped. And of course, just as always, if you have addition and its inverse happening in the same problem, we'll work it from left to right. Okay, that's way too many words for math class. So let's start doing some example problems. Okay. I'm trying to close this little chat window that I had up. I hope it's not recording. I can't. Okay, so clear this screen. Let's start with some example problems. Let's start with the simplest of example problems, the ones that all students usually get wrong. when they're first starting. So this is a really simple order of operations problem. And whether you were taught the dreaded PEMDAS way, or you just learned order of operations the first time from me, or some teacher taught you another way, I bet that you know that you have to work multiplication before you perform addition. So again, whenever you have more than one operation, can you see that I have more than one operation in this problem? I hope that you can see my operations. So let me pick out a different color here so that I can emphasize my operation. I know that the order of operations is going to come into play because I have more than one thing to do in this problem. I have addition and I have multiplication. Anytime you have more than one operation to perform, you have got to follow those steps. So first step, grouping. There are no groupings here. I haven't used any kind of a symbol to pull some numbers apart from the rest. And so that's a moot point. Next step would be exponents. Well, I see no little floating numbers. I see no radicals, no powers, no roots. And so I have no exponents here. So my next step is multiplication and its inverse. Multiplication and its inverse division. So do you see any multiplication or division in this problem? Absolutely, right here we have 7 times 3. And so this, in fact, let's get a highlighter to pull this out, because if you're a student who struggles with math, most of us struggle because they can't see what they're doing. So do you see that? I just highlighted 7 times 3. 7 times 3 is the part of the problem that I'm doing. And I know that 7 times 3 is 21. And so what I've just done here is I've replaced this part of the expression, 7 times 3, with something that's totally equivalent to it, 21. Now, it's really important in algebra classes, especially as you do, whether you're doing equations or you're dealing with expressions or anytime, that each line is equivalent to the line before it. So this line should equal the one above it. So it's really important. I have this 21 here that's equal to 7 times 3, but I don't have my plus 5 from above. And so what I'm going to do is I'm just going to drop down the plus 5. The stuff that I haven't used yet will just drop down. A lot of students will say, well, why didn't you drop down the 7, Kate? Because I already used up 7 times 3. That answer is right there. Okay. And now I have a new step. So each, I forgot to write this. This line should equal the next line. All lines are equal. Okay, sorry. And then we're just going to do one step per line, okay? And we'll look at some exceptions to that. I know there's sometimes when it doesn't matter, but for the most part, general rule, if you're not sure, we're going to do one step per line. Now, so I'm going to now do here the last operation, the only other operation I see, and probably you guys don't even need me to do this, but I'm just going to pick up my highlighter for my students who struggle with this. Next thing I'm doing now is this 5 plus 21. And once again, just like I did before, my answer goes underneath. I know that your third grade teachers taught you to go across with your answers, but what I found is that students who go across an equal sign with their answers really, really screw up later when we do something called solving equations in algebra. And so I would beg you to retrain your brain to go down. Answers to expressions go right underneath. Okay, and don't worry, I know where to look for your answer as your math teacher. I'm going to look at the bottom of the problem, not the right, okay? And so this is my answer. My answer is 26. Okay, I'm going to pick up my speed a little bit. Let's try some more complicated problems. I just want to, this one is actually not that much more complicated, but I just wanted to say to you, remember how I said most of the time we just do one thing per step? And it's true, but mathematicians are super duper lazy. So let me just show you here. Once again, on this problem, I have 2 different operations. Whoops, not what I meant to do. Maybe I should say I actually have 3 operations, even though there are only 2 kinds, because I have this multiplication, this addition, and this multiplication. Now, what we already said was that we would do our multiplication before we do our addition and its inverse. We're going to do multiplication and its inverse before addition and its inverse. So I am going to go ahead and do my 5 times 3 first. But I want you to notice that in this problem, there is another multiplication problem. Can you see it? And they share absolutely no numbers. There are no numbers being shared. Can you see that? Because these two problems are totally separate, sharing no numbers, I could just go ahead and work them at the same time, and I will. So 5 times 3 is 15. 6 times 4 is 24. Now I replaced this expression with an equivalent expression. I replaced this part of the expression with something equivalent, but I have not yet used my plus, and so my plus drops down so that my two lines can be exactly equivalent or equal to each other. And now I will do my final operation here, which is obviously just to add 15 and 24. That's not tricky to see. And let's see, hopefully I get 39. Okay, wonderful. Now let's look at an example that students who traditionally use PEMDAS or who usually use PEMDAS traditionally get very, very wrong. So here is my example. Whoops. I'm just going to change a number. Okay, so here's my first. Remember, I told you I have a few issues with students who memorize. Please excuse my dear Aunt Sally. So I'm sorry that I keep mentioning it for those of you who never heard of this in your life, but I always have to convince the students who learned it this way that it's actually a broken method that doesn't always work. So take a look at this problem here. I have 12 divided by 6 times 2. And what a student who's learned PEMDAS will tell me is, Kate, PEMDAS, multiplication has to come before division. And so they will want to wrongly, so don't do this, start right here. Okay, really common. They're like, I'll do the 6 times 2 first. Okay, now that would be incorrect. Please do not do that. Remember what we said. So here's my order of operations up the top right again. I have to do any groupings first. I don't see any groupings in this problem. Then exponents. I don't see any exponents, okay? But then we said multiplication and division were part of the same step. If you're working on part of the same step, you need to work from left to right, regardless of if it's multiplication or division. And so I will do this first. Now this time it really does matter which one I do first, because you can see that these two problems share a number. 12 divided by 6 and 6 times 2 share this same 6. This same 6 is involved in both of these operations. And so it's going to be really important that I move from left to right. And so that is what I'll do. And let me switch out of red so you don't suddenly think I'm doing my work wrong. But if I do 12 divided by 6, I totally switched conventions. I've been highlighting it and then I started underlining it. So I'll keep highlighting. If I do 12 divided by 6, I'll get 2. Now what haven't I used from above? I have not used the times and the 2, so those will drop. And then you can obviously see that the last thing I need to do here is do my 2 times 2. And of course, 2 times 2 is just 4. And I'm sorry that's really small at the bottom of the screen, but it's because my toolbar is in the way right now. Oh, there it is. I'll make it look right. I'm getting smarter and smarter about how to use this iPad every day, y'all. Okay, so I can see my final answer here is actually 4. Now, I have students all the time who say, Kate, it doesn't matter. I could have done it the other way. I would have gotten the same answer. So there's homework for you. I'm curious. If you had done the multiplication first, would you have gotten the same answer? Pause the video, find out. I assure you, you do not. And only one of us can be right. There's not a couple multiple different ways to do this, and one way's right and one way's right. Only one of us can be right. That's why there's the order of operations in math class, so we can have a convention of about how we're all going to work a problem so we get to the same place. Okay, let us go ahead and look at how order of operation problems can get trickier and trickier. We've seen some super simple examples that you probably could have done in 4th or 5th grade. Let's get to some complicated examples. Okay. First one I want to look at is one that comes up all the time. In algebra, real popular format, it just happens a lot for various reasons. But here I see this expression, and people don't know how to read this, so let's read it together. This says 2 times the quantity of 5 minus 3. So when I say times the quantity, I'm saying times all of this, not just a 5, times all of that. So times the quantity of 5 minus 3 squared. I read that little floating power 2 as squared. You could also say to the second power. Okay, so 2 times the quantity of 5 minus 3 squared. What I found in algebra class is if you can read it, you guys can do it. A lot of times you can't do it because you don't know what it says. You don't speak my language. So practice reading your expressions. Plus, that just happens on the GED. They have problems where they ask you to translate math into English and English into math. If you don't know my language, you'll never be able to do it in a million years. Okay, so 2 times the quantity of 5 minus 3 squared. Okay, so let's look at our order of operations here to see what our first step should be. So you know that we had said that we would do any groupings first. And this is the first problem we've seen that does have a grouping. And it's really traditionally what we often think of as a grouping, because this particular group is set off from all the other numbers using parentheses. And so that's where we're going to start at the inside of this grouping. I have a group 5 minus 3. So 5 minus 3 is 2. Now, remember I said that parentheses are not only used for grouping, they're used for other things as well. As most of us know, that when two numbers are shoved together, maybe I should get a different color out. No, I'll just highlight this too from above. Okay. When two numbers are shoved together, like these two are, with nothing between them but parentheses, that's an act of multiplication. So I'm going to keep my parentheses because I have not yet done that multiplication. And I'm going to drop that 2 from above that I haven't used, and I'm going to drop that power that I haven't used. Do you see how my expression is exactly equivalent to the one above it? I just replaced 5 minus 3 with an equivalent piece too. Okay, now according to my order of operations, after I finish any groupings, I'm going to do any exponents. And remember that exponents are both powers, little floating numbers, and their roots, those radical signs. And so I can see here on this particular problem that I have a exponent. I have this 2 squared. Okay, so 2 squared is the next thing for me to do, and I will drop my answer underneath. 2 squared is 4. Now, an interesting question, do I still need the parentheses? I sure do, because I have not yet done this multiplication up here. And so I'm going to drop, my 4 is going to be in a parentheses, and I'm going to drop this 2 that I have not used. Okay, and now it's obvious to see what to do next, because there's only one thing left to do, and that is multiply. So 2 times 4 is 8. Wonderful. If any of you have trouble seeing order of operations problems, I highly suggest you do them with a highlighter so you can see what you're replacing in each expression, and you will get way better at doing substitution, which is a principle we use all the time in math class. Basically in math class, anytime two things are equal, we can swap one out for the other. We can swap one out for the other. We do it all the time. Happens in algebra, happens in these order of operation problems. It's going to happen so much. And you can see that's what I did. I swapped out 5 minus 3 for a 2. I swapped out 2 squared for a 4. And then I swapped out 2 times 4 for an 8. As I came down this problem, this expression, as I simplified this expression. Okay, this is called simplifying, by the way. A lot of students think it's called solving. This is not solving. What we are doing here is simplifying. Simplifying. I want to say this because it is like my pet peeve when people abuse the word simplify and solve and they don't know what they mean. So simplify means to perform the indicated operation. You're like, what? It is what we usually do in math class, at least before algebra. We're pretty much always doing what we're told. Let me show you what I mean. Like here, there was a minus sign up here, and what did we do? We minused. And then here, We saw a power, and what did we do? We raised it to a power. Here, we saw the symbols that told us to multiply, and we multiplied. So what I mean by perform the indicated operation is obey the signs. Now, you might be saying, Kate, of course we obey the signs. Well, actually, later in algebra, we'll see some times where you get to be disobedient to the signs that you see, and that'll be interesting. But for now, the only thing we can do with a problem like this is just do what we're told, obey the signs, and that's what we're doing when we're simplifying, okay? Okay, so let's look at another tricky example that messes with a lot of people. When they see fractions get involved, people will lose their snot. They will just freak out. Okay, so here I see the problem. I would read it like this: the sum of 5 plus 3. When I say the word the sum of 5 plus 3, I'm talking about this entire portion of the problem right here. This is the sum of 5 plus 3. I want to take all of that and divide. Did you know that a fraction bar means the same as divide? So it's the sum of 5 plus 3 divided by 2 squared. And that's what I see right here. Now remember what we said. We said a fraction bar naturally breaks things into 2 groups. We have a top group and a bottom group. It's going to be really important that you deal with the groupings before you deal with the fraction bar. And so that is what we're going to do. So 5 plus 3 is 8. And I have not yet dealt with my fraction bar, so it drops. And 2 squared is 4. Can you see how I did the math on the top? I did the math on the bottom, and I saved the fraction bar for last. And now students are like, Kate, you haven't even taught me fractions. They get all mad at me. But hello, this is not a fraction problem. 8 divided by 4, it divides perfectly. There's no reason to leave a fraction on this paper. It simplifies very nicely. 8 divided by 4 is 2. So if you didn't know that, make a note to yourself that a fraction bar means exactly the same as divide. Now you might say, Kate, how could that be? Like 3/5, does that really mean 3 divided by 5? Well, it sure does. I'm just too lazy to do nasty division. It doesn't divide perfectly, so I leave it as a fraction. So if I was doing something like that, I might not do the division. I could, but I might not because I'm lazy. Really, fractions were invented so lazy mathematicians don't have to deal with decimals, nasty numbers. Okay, there's a ton going on in this problem. I really, really like it. And because this is actually similar to things that come up in math a lot. So let's take a look at simplifying this sucker here. Okay, so I'm going to grab my highlighter. Okay, now can you see that I have a natural grouping here? So basically I have this square root symbol, which has naturally set off part of my problem from the other part of my problem. So remember that whenever we start with inside of groupings. But the tricky thing about this grouping is even this grouping has 3 operations in it. So let's look at the 3 operations that are currently inside of my grouping. So the 3 operations inside my grouping, there's a, not what I wanted to do. Oh, no wonder I have my eraser out. So there is a square. That's an operation, raising something to a power. There's a minus sign. That's an operation, subtraction. And there are these 2 numbers that are super, super close together with the only thing in between them being a parentheses. So that's an act of multiplication. So even inside of my grouping, I have 3 different operations. So which one should I do first? Well, like I said, even inside of the grouping, the order of operations applies. So there's no groupings inside this grouping, but there sure are exponents. So let us deal with any exponents first. So here is an exponent, 5 squared, and it is 25. Now, I have to tell you the truth. I am a mathematician and I am lazy. And here's what I notice. This 5 squared, and the next thing I would do, so no, after exponents comes multiplication. So the next thing I would do, do not share any numbers. Can you see that? Those 2 parts of the expression are totally separated by that nice minus sign. Because they don't share any numbers, they don't affect each other. So I could do them both at the same time. Here's where you are legit allowed to skip steps. And so that is what I'll do. I will do them both at the same time. I'll do 4 times 4 is 16. And again, the reason why I can do this is because they share no numbers. If they shared numbers, I would have to do the exponent first and then do the multiplication in the next step. Okay. Now, I have not used my minus, so it will drop. I have not used my square root, so it will drop. I have not used my minus, so it will drop. I have another thing that's kind of just separated off by itself, 2 to the 3rd power. If I wanted, I could really do this now too. So if you do it, no big deal. But I'm just going to stay consistent so it doesn't freak people out for now. And I'm going to keep on working on my groupings. So like we said, we have to finish our groupings in our problem before we do anything else. So I'll do that now. 25 minus 16 is 9. Okay. I have not used my square root. It is still here. I have not used my minus. It is still here. And I have not used my 2 cubed. It is still there. So now I've finished the groupings in this problem, done with all the groupings. Next step is exponents. And remember, exponents are both those little floating numbers and their roots, or these radicals. And so I have 2 of these in this problem, and once again we can see that they share no numbers. They're separated by a minus sign, they share no numbers, so it really doesn't matter. I can work them both at the same time because they're not related. So most students here are going to do a very foolish thing. They're going to write 6. They're not writing 6 because they don't know the order of operations. They're writing 6 because they're thinking so hard about the order of operations that they forget how to do exponents. So don't forget how to do exponents. Let's come over here so I can remind you, what does it mean to take 2 and raise it to the 3rd power? It means to multiply the number 2 by itself 3 times, not to multiply 2 times 3, but to multiply 2 by itself 3 times. So we know that 2 times 2 is 4. And if I were to multiply that 4 by another 2, see that 2 from above, it would give me 8. And so it's important to be able to see that 2 to the 3rd power is not the same as 2 times 3. 2 to the 3rd power is 8. Now, if you're a beginning student who doesn't have this memorized or forgets this, you are going to have to come over here and do your side work. But do not mess up your order of operations problem with all this drama and side work. I don't want to see this. I want to see your beautiful equivalent steps, okay? So you come do that out to the side if you need to do that. Okay, so I replace my 2 to the 3rd power with 8. I have not used my minus, it drops down. And the square root of 9, I'm asking myself what number times itself equals 9? And of course that's 3. If you don't know that, what you need to practice is square roots. And I'm not going to get into it here, but that's the concept. Okay, so now, next thing, 8 minus 3, that is the last thing to deal with, easy enough to see. So 8 minus 3 is 5. Okay, brilliant. I think that I'm done with this order of operations. And so if you have any questions, be sure to ask them. If you want a worksheet or practice on this topic, let me know. I have different levels of practice. This does frequently occur on the first 3 problems of the GED. When it does, it often has cubes, cube roots, and I mean the first 5 problems of the GED, by the way, or negative numbers involved. Okay, and so you really are going to have to get up to a high level of understanding with these order of operations problems. But I do have problems at different levels for different learners.